Okay. Hi, welcome everyone. It's really a big honor to have Professor Craig Knoblock from University of Southern California to give us a talk in the Semantic Technologies Committee's webinar series. And today he will give a talk on the topic of exploiting semantics for integrating data on critical minerals. Okay, to save time, I will just give the floor to you, Craig.
Okay, great. Thanks. Okay, welcome everyone. I'm going to be talking about this, explaining semantics for integrating data. And, I welcome questions as we go. So if, something's confusing to you, don't hesitate. You can raise your hand. Hopefully I'll see you if you raise your hand or just interrupt me. I welcome the questions as we go. Okay, so here's the outline of my talk. It actually, I've planned about 30 minutes, so, I only have 1 or 2 slides each of these topics. I'm first going to talk about this general problem we're working on finding critical minerals. This is part of a USGS DARPA program that we're currently involved in. And it's quite a nice, interesting topic, and one where, explaining the semantics of data is extremely valuable here. So I'll talk about the sources of data that we're dealing with in this case, which include things like mining reports. So then we have to worry about, well, how do we actually extract data from mining reports? Then we have lots of tables of data that come from various things like papers, and we have to extract the data from those and make sense of that. Then we have to do what's called entity resolution, which is figuring out, when you pull this data from these different sources, which of these sources actually refer to the same entity. In particular, which of them refer to the same mine or mining site. Now, once we have all this data and we've sort of made sense of it, then we need to load it into the knowledge graph that we're building. And then I'll talk about how we're going to basically build and query that knowledge graph and then create the gradient and tonnage models from that. So let me dive in. All right, so what's the problem here? So as you all probably know, right, critical minerals are critical for transition to the green economy. We have all these minerals that are in high demand now because we need them for things like batteries, lithium, cobalt, nickel, tungsten, and so on. And they're often in short supply, and we depend on other countries for them. So one of the things the US would like to do is to actually find more domestic sources of these. So DARPA and USGS basically created a program that is focused on sort of using AI technologies to address these problems. And there's really 3 parts to this program, and I'll just mention them because they're all relevant here. One is on actually taking historical maps. These are historical geological maps, and extracting the data from those maps. And this is a topic that we're working on as well, but I'm not actually going to talk about that today. The second topic that they're working on in this program is creating what are called gradient tonnage models of these various commodities. And I'll get into more details about what a gradient tonnage model is in a minute. And then finally, all of this information from the combination of the maps and all of these different sources of information from these gradient tonnage models is then used to basically predict the most productive locations to mine for these minerals. And so I'm going to focus on our work on topic area 2 today, which is very much about, building a knowledge graph of all this data. But a little bit more about the problem first, right? So what happens here is that we're given a particular commodity and a deposit type for that commodity. A deposit type refers to the type of geological formation that basically created that particular deposit. What they want to do is create something called a gradient tonnage model, and this is really an example of this is shown on the right, and this is basically what this graph on the right shows you. Is on the x-axis is the tonnage in millions of metric tons. The y-axis is the gradient percent, and this is for a particular mineral, in this case tungsten skarn, that they're interested in. And then on the chart itself, each of the labeled points corresponds to a mine that is currently or has previously extracted this particular mineral. And the reason they're interested in these gradient tonnage models is so that if they're trying to evaluate a particular site for possibly mining, they have some idea of how much material they can expect to find in that particular type of location. So these are very valuable for doing that kind of prediction, so they can go after sort of the most productive mines. So our goal then is to actually put together the data. To actually create this. And why? So it turns out that right now creating these gradient tonnage models is this very laborious process, involves assembling data from many, many different sources. If you look at for example, the mining reports where some of the data comes from, these reports might be, 500, 600 pages long, where the data is sort of buried in the report. So it's a task that takes many months of work. One geologist in this area characterizes as a soul-crushing exercise, so one that's well suited for a computer to support. So our challenge then is to actually apply sort of AI and machine learning techniques to this problem so we can automate this work. So our approach then is to essentially exploit the latest machine learning techniques to solve the different pieces of this problem, right? So first, one area we're working on is exploiting what are called large language models. These are these big AI models that have gotten all the press recently, but they're really ideally suited for extracting data from these large documents and things like company reports. The second area is doing what we call table understanding and applying that to ingest data from various tables. And there's a lot of tables of relevant data here because many people have worked hard to sort of compile this information in the past, but it's a matter of actually understanding that information and pulling it together. And then the third area is using what are called spatial language models to essentially combine the data across these different sources. Because one of the problems is that as soon as you pull data from these different sources, the problem is now you need to figure out which of these sources are actually referring to the same location, right? The same mine. And so that's a non-trivial problem. And so another piece that we're working on. And then finally, the last piece of this is then creating and maintaining this mining knowledge graph for constructing these gradient intent models. And one of the key ideas here is that by automating much of this processing, previously someone would do a study like this and they would put out a report and it would be, the 2019 gradient tonnage model for tungsten. Well, in a few years, that's out of date. One of the nice things about automating all of this and putting it together in sort of a system like this is that you can essentially create something that's much more maintainable and can live over time and be continually updated. Okay, so that's the general approach. Why is this important? I mean, the idea is that, this is going to produce the technology for rapidly building and maintaining these high quality gradient tonnage models and what are called mineral site data. As I said, it means that, as new information becomes available, it can be quickly updated. And then the resulting information then can be fed into these other tools for doing what's called prospectivity mining, which is predicting promising locations for building the next mines. Okay, so here are the sources of data that we've been working with for this project. So first I mentioned, we've mining reports. These are come from the mines themselves. And the reason that these are quite valuable is that many mines are publicly traded. So the mines themselves have an incentive to actually put out all this data because they're trying to raise money. And then it turns out that Canada has a very detailed requirement for, what has to go into a mining report. So a lot of the mines sort of follow this format and stuff. So that standardizes the information a bit, what they provide. So that's one source of the information. A second source of the information is tables. And these are tables that typically come from people that have done various kinds of studies. Usually they've written a paper about it, and maybe they've done a study about zinc or copper or tungsten or something like that. And then they'll compile this very detailed table of information, which is really valuable. But one of the things you'll see about these tables is they're very, very complicated. So one of the challenges is actually making sense of this information and being able to relate it to the other sources of data. The third source of information are basically databases of mining sites. And these are two example databases from USGS. One is called USMIN, which is a more recent database of this information. Another one's a historical one called MRDS. But there's many other ones. There's all of these databases that come from the individual geological organizations within each state. So USGS is the national organization, but each state has their own geological organization and stuff. They often compile their own databases by state and stuff. And so there's a lot of data here to be mined as well. Okay, so, but one of the things, this is a talk about semantics. And so one of the things that of course we have to do is have some kind of shared domain ontology. And this is a little bit of an odd representation of it. That's partly because we're working with people that are not all semantic web people, but essentially, we have a set of classes and relationships here which correspond to our domain ontology. So a mineral site is sort of the top level thing, which is the mineral site would correspond to the actual each of the individual mines themselves or other specific sites where that mineral has been found. Then you have what's called the mineral inventory. This is the information that you would typically find in the mining report or in the database, in the Excel tables or various tables of information. And this is detailed information about a particular information that's been found. In particular, it would include the commodity, the deposit type, the amount of the material that was found there, the grade, how much contained metal was there, and then some kind of reference, right? And then the reference would tell you, well, where did this information actually come from, since we want to make all this reproducible. So, maybe some from some document on some page, and then there's the bounding box where the information is found. And then the link to the document would be the actual publication reference, right? Where this information was extracted. Other information that's sort of related to the mineral site would include the location of that site. So this would include detailed information about the lat-long coordinates and country and state it's in. And then we also have things like the geological information, which is, maybe some more information about the actual process that created this type of formation. And then separately up at the top, we have mineral systems, which then relate to sort of things like what's called map criteria and stuff, but we won't get into that today. Okay, and Marshall mentioned at the beginning, some of you may have heard that, USGS has a domain ontology and they have their own knowledge graph. So we really are building on top of theirs. So, we start with the USGS GOKB, and then, everything we've done is sort of an extension on top of that. Okay, so now let me get into the details of what we're actually doing here. So here, first, I mentioned that we have these various mining reports. These are sometimes referred to as 43-101 reports, which is the standard that the Canadian Stock Exchange uses for these mining reports. And we have access to many thousands of these kinds of mining reports over many, many years. Which is very useful because, one of the challenges here is that if you look at the most recent mining report, that's going to tell you how much material they think is still in the ground that can be mined. But for our purposes, we want to know for any given site, what's the total estimated amount of material at that site, which would include all the material that was previously mined, as well as all of the material that may be still underground. And to get at that, you really have to look at not just the most recent report, but in fact, the entire archive or history of this mine, so that, each year they would report how much material was extracted. And so we'd want all that information as well. So then the question is, all right, so let's say you have text documents, and this, I'm talking about mineral sites and data about minerals, but most of what I'm going to talk about today could be applied to almost any application area. And I think there's many other areas where this is relevant too. So, but let's assume you have a text document, and now I have specific information I want to get out of this text document. This is really greatly facilitated by some of these recent work, in particular, the kind of information we want to get out of here. So I mentioned that, we have all these technical reports, but, these documents are long. So we have, this example here comes from a 150-page mining report, and buried down in the details here, it sort of has the details we're looking for. Like it'll say, okay, Highland Valley Copper, the copper production in 2022 was 119,000 tons, and then in 2021 it was 130,000 tons, right? So our goal is to extract out this very specific kind of information from these reports. And it's, a relatively small amount of information, but the challenge is actually finding it in these very large documents. So I did a little example here. I ran this through ChatGPT, which is, one of the AI models built by OpenAI. And here I gave it the query. I said, okay, I asked it to extract the total amount of indicated and inferred resources and corresponding grades from the following paragraph. And then I just copied this paragraph that here starts with table 1413 directly from the report itself. And as you can see, it does a very nice job at this, right? So it actually says, oh, okay, from this paragraph, the total indicated resources is 505,000 tons, and the grade for that is 0.468% WO3. And then the indicated inferred just referred to how they're in the mining jargon, whether or not they think it's likely, or whether indicated is sort of likely, and inferred means they've actually drilled a bunch of holes to actually confirm that that much material is there. And so they often want to know the combination of these things. So for researchers, 280,000 times. This is pretty nice. It was able to take a fairly complicated paragraph and pull out the right information. But of course, in this case, I have a report that's on the order of 100 pages. So I tried another example here. I actually signed up for GPT-4, where you can actually give it the entire report. In this case, I took a report from this mine, the Fox mine, and I basically copied it in. I just, dragged it in here. And then I gave it the same query. I said, okay, extract the total inferred indicated amounts and coordinate grades from this report. It had to think for a few seconds and came back and actually gave me this nice breakdown. Okay, here's the tonnage, the grade, and also gave me the contained metal, which I didn't ask for. It's interesting it gave me that in this case. But you can compute the contained metal. It's really just the multiplication of the grade times the tonnage here. And likewise, same thing for the inferred resource. So this is quite nice. The tools are getting quite good. You can ask it questions like, oh, well, what page did this come from? Which I discovered doesn't always give it right. Give the page numbers or have some weird formatting on them. But you can ask questions like, give me the paragraph that the information came from, and it'll actually pull up the paragraph. And so you could then search that in the report and stuff. So there's ways, one of the problems that people have been concerned about with using these kinds of models and stuff is, what's called hallucination, where some of the information it makes up. But there's ways to sort of now validate this information once it comes out of here. And, now that you can actually find this kind of data. The other challenge here is coming up with the right prompts, right? This is the query that I put in here. I had to actually formulate the query in a way that it would actually give me the information that was needed and stuff. And so there's still some challenges to make this work, but as you can see, the tools really take this whole extraction of data from text documents to a whole new level. So this is the first step in terms of our processing, which is to get the information out of the text documents. The next step is actually extracting the data from tables. So here's an example table. This comes from a paper called The World's Lead Zinc Mineral Resources by Mudd, Jowett, and Werner. The table is actually just another document that's provided with the paper. So you can actually just download this entire table. So this table is great because this basically has every lead mine in the world by location, and then includes detailed breakdowns of the metric tons of the ore, which is MT ore, as well as the breakdown for each of the different commodities in this mine, what's the grade of that commodity. And from that, you could then compute the amount of contained metal for each one of these. So this is really valuable information, but it's a little complicated in terms of how this table is organized and stored. And again, we want to basically pull this information together with the mining reports and all of the other database information that's available about this. So we developed this system called SAND. One of my students has developed this tool. And it's basically a tool for creating models of structured sources. And the way this tool works is really quite interesting, which is that here we have at the bottom, on the bottom left, is this table of information. I'm interested in actually building what's called a semantic model of this table. I want to know what the mapping of this table is to a corresponding domain ontology, right? So I have at the top here some set of algorithms for doing this mapping. The student's algorithm is actually called grams. And then we use an existing knowledge graph called Wikidata, which has a lot of structured data already contained in it. And then the idea is to actually try to do as much of this mapping as possible automatically. And the way this works is by looking for sort of overlap in any of the information here with the information that's already in Wikidata. And it may turn out that there's information about some of these rows of data that's already in Wikidata. And then we can use that to help us actually create the model of the data. And then it will show the user sort of a visualization of that mapping. And then there's a nice user interface where the user can then go in and edit the mapping and stuff. But when you're done, what's really nice is that then you can basically say, okay, now I just want to turn all this into what are called triples, right? Which, if you're familiar with the semantic web world, this is basically this RDF representation of the data, where we essentially started with a structured data on a table where, none of it was, we didn't know the semantics of what each of these columns correspond to. And then when you're done, it's mapped into this shared domain ontology. The one I mentioned earlier is the one we'd use for this project, and then can produce all the data in this triple representation. Okay, so here's the way this approach works in this project. So we take this information from like production reports. So here's a table of data that comes from one of the mining reports. We have other background knowledge that comes from things like documents. So there's a USG document about mineral deposits. So we have this sort of larger mineral knowledge graph, which serves as an input to this SAN system. And then it takes the information here and it can recognize that, oh, these things are mines. It might recognize other kinds of information. Numbers are harder. So usually numbers, you may actually have to tell it exactly what they represent. But it tries to figure out as much as possible what the information is contained in these tables and stuff. And then it produces a extract information, model it. And then once that's done, it goes back into this mineral knowledge graph, which then can help it map the next data set. And so that's the sort of the underlying idea behind sort of the table understanding that we're using here. The result is a model of the data itself, right? So I mentioned the top level, we have a mineral site, and that's going to have things like the location information and the deposit type, and then it's also going to link to the mineral inventory. The mineral inventory has information about the amount of ore in there, and then the different commodities and their corresponding grades. Right. And so all of this information gets described in this sort of model, and then the system can then apply this model to automatically generate the triples or RDF representation of the data. Any questions so far? Okay. All right.
Well, I have a quick question.
Sure.
Yes, Craig. I found it very interesting that you found GPT-4 can just parse the PDF you upload to it, and it will answer the question. But I want to know the file size or how many pages of the report you upload to it.
That particular report was 78 pages long.
78. Okay, that's quite a lot.
Yeah, it's quite large. I mean, I should play with it more because we have some other reports that are like on the order of 600 pages. But I don't think there was any limit in the size now. That's part of, one of the big differences that went from GPT 3.5 to 4, which is that you could give it an entire document.
All right, thank you.
Sure. Okay, so the next challenge then is dealing with this entity resolution of the mining sites. So there's quite a few different databases that contain information about mining sites. USGS has a couple of these. One's called MRDS, and that goes back from many, many years, maybe on the order of 100 years or something like that. But they stopped maintaining it some time ago. But historically, it has a lot of good information. And then a more recent USGS database, it's called USMIN, which has specific commodities and fairly comprehensive information about those specific commodities. So the list so it's much less comprehensive than MRDS, but much more current. But the challenge is, and then here on the right side, you can see that some of the same information is sort of superimposed on this map. And then the question is always, well, which ones of these are actually correspond to the same mine, right? This Menke mine, is that the same as, all three of these, are they all correspond to this one Menke mine here? So this is one of the big challenges, is when you're pulling information from these different sources, not just these databases, but also when I pull it from the Excel table, or if I pull it from a mining report, I need to make a determination about, okay, is this talking about the same mine or a different mine? Which ones are the same? So you can use the combination of the attributes of the information along with the spatial information about this. And so this is work being done by my colleagues at University of Minnesota that are working with us on this project. And they have built this spatial language model. They call it SPABERT, which is, is built on top of BERT, which is one of the earlier language models. And then the idea of this was to capture sort of the spatial varying context of the points that you're interested in, where it could then figure out how we could link these points of interest across different data sets. And what SPABERT does is it basically hypothesizes what we know about a point of interest characteristics by its surrounding point of interest, right? So it's sort of using the surrounding context to help it figure out, okay, which things are likely to match. And this is kind of analogous to this idea that knowing word meanings by using their linguistic context. And there's an example down here, which is sort of, the bottom square boxes correspond to different instances of data about University of Minnesota. And then all of these are sort of related by all of these other points of interest and so on. And so here, this SPA-BERT thing basically creates this this language model that encodes all of this information, right? It basically creates this vector representation of all this data, and points that are close by are going to be closer together in the vector stuff. So now when I'm giving some set of points, then I can use that to sort of figure out, okay, which ones of these are going to be most likely to be related. So that's sort of the technique that we're using here to sort of bring this information together from all these different sources. Then that brings me, okay, so now we actually have to turn all this information into the knowledge graph itself, right? And so each of these data sources is basically going to be mapped to this ontology, right? I presented the ontology early on, and we're going to use that to produce an RDF representation. That's a triple representation where everything is represented as a subject, predicate, and object. And the reason this is important is it's not just that it's subject, predicate, object, but it's a subject, predicate, object using this controlled vocabulary of the ontology, right? So we gave it the ontology, we mapped all the data to this ontology. So now when I put all this into this representation, it's all using the same terminology so that I can combine the information across the different sources. Both SAND, the tool I mentioned earlier, and we have an earlier system called Karma, which I included the link here because they're both useful tools for actually doing the mapping of data sets. Karma is actually released, it's open source. If you go to karma.isi.edu, it'll take you to our website, and it's a very nice tool of basically be able to take a data set of data and very quickly map it to some domain ontology. SAND is not yet publicly released, but will be shortly. But anyway, these are all tools just for creating mapping data sets into this triple representation. And the idea is that what I showed you earlier, right, with the extraction of the data from the documents, the extraction of the information from all the tables, these databases, so they're all been mapped now to this one shared domain ontology. So we have this large knowledge graph of all the data. All that gets loaded into a triple store, which is basically this database of triples. And then I also mentioned we, try to figure out, okay, which of these sort of entities, the mining sites that we've extracted information about, are the same, right? We have to decide the same. And so when the software determines that, okay, these two or this set of mining sites correspond to the same entity, then we assert these same as links, which is sort of a standard representation in the semantic web world, where I can sort of assert that certain things correspond to the same entities. And then I have all this information in the knowledge graph, and now I can do queries on it, where I use the query language called Sparkle. And Sparkle is a lot, if you're familiar with SQL, it's a lot like an SQL language, but it's an SQL language for a graph database. So triple store is basically a form of a graph database. Okay, so that's the basic knowledge graph we create. But here's what that looks like in terms of the application I've been talking about. So I've built up this large sort of critical mineral knowledge graph. I create a set of Sparkle queries that will essentially generate tabular data, right? So it's going to say, okay, here's the set of mines, here's their location, the commodity, which in this case I'm interested in zinc, the tonnage for each one of these mines and the grades. And then that information, we can then take this, and in fact, there's various software libraries out there where then you can take this information and then build this traditional graph of this information for human consumption. But for the computer, it's probably quite happy looking at this form of representation of this. And as I mentioned earlier, right, they really want these kinds of gradient intelligence models because this helps you figure out, okay, now if I find a new site that's of this particular type, which is, if this is, MBT zinc or something like that, then I can say, oh, well, if I wanted to predict how much material, what kind of grade I expect to get, probably is going to be somewhere in the middle here in terms of, I could estimate the combination of the metric tons and the grade for that. Okay, so project status. So this is a project, we're 5 months into sort of an 18-month long project. So we're still working on the data extraction, modeling, and linking. We have initial working components of all those, but it's, at this point, we're still trying to get all the pieces put together. I think we'll complete our first sort of complete gradient intelligence model sometime by the end of January or mid-February or so. And we're doing that for MBT Zinc. That was the one that was chosen as the first test. But once we have that, then we have all the tools in place that we can rapidly build these for other commodities. Some of the challenges that we've encountered in terms of addressing these problems are one, locating the source information, right? So we have a lot of experts involved in this program, so they're really good at finding that. But one challenge is, well, how do you find this information more generally, right? How could you go out and actually locate this information automatically? Because it's really scattered all over different websites, different in different reports and so on. And so one question is, how do you actually locate this information automatically? Second one is, how do you accurately extract the information from their mining reports? I mean, I showed you a nice example that it found the information very quickly, but sometimes the information is more complicated in the reports. There's multiple places where it mentions it. And so sometimes making sure that you're getting the accurate information can be a bit of a challenge there too. Third thing here is automatically modeling of the tables themselves, right? So I showed you some example tables and we built a model of that. And then the challenge for us, of course, is, well, how much of that can we do automatically, right? So, and how much, user interaction. So we have a nice tool. So if we can't automate it completely, we have a nice tool that the user can then work to sort of refine the model, but that can take time and require some more expertise. And then finally, this ability to accurately link the entities across different sources. And this is challenging because, well, oftentimes the amount of information that you have is very limited. You often don't know that much about the particular mine or even the given site. And so knowing definitively whether or not it's the same one can be actually hard. So these are all challenges that we're wrestling with and, addressing part of the project. But I think this is an application that presents a nice example of sort of the power of using sort of these semantic techniques to pull all this information together and turn it into something that's actually much more useful. I just want to acknowledge the rest of the team. So this is not all my work. So at USC, I have a number of students that help me with this. I have 4 students working on the project with me. And then we have collaborators from Infralink, which is a small company that's actually working on the extraction information, and University of Minnesota that's working on sort of the entity resolution piece. And then we have a consultant, Simon Jowett, who's an expert on this topic. I mean, he has built his own domain models and many reports on this topic and stuff. So we have our own domain expertise here. So, okay, I'm going to stop sharing and then open it up for questions.
Yeah, thanks a lot, Craig, for this wonderful talk. We have a lot of time for questions and comments.
Okay.
Yeah, I got a question about the Sparkbird.
Sure, go ahead.
And I just wonder, how does the Sparkbird handle the scenario where a mine point is geographically located between 2 distinct mineral deposits? Or does it attribute to the mine to a single deposit, or can it recognize and represent the mine relationship to the multiple deposits?
Yeah, no, that's a really good question. And one of the challenges we have, and I think we're going to have to, work on this sort of in the next phase of this project, is that mines are often organized into zones. And right now we don't have a representation of a zone because some kinds of deposits actually are located over extremely large areas and stuff. And so I think we'll have to extend our representation and make it a little bit richer so that we have the notion of a zone and that we can reason about the larger locations and stuff. I think right now it'd be very easy for Sparkbird to get confused. But it's partly just a limitation in terms of the current representation, because mines aren't really points, they're really regions. And so we need to, well, in the next phase, after we get the initial version working, we're planning to sort of extend the representation of that.
Okay, thank you.
I was wondering if I could ask a question.
Sure, please.
Yep.
So, hi, Craig. I really enjoyed that talk. As someone who works in knowledge graphs as well as geophysics and earth sciences, I really see the huge value in the work that you're doing. And I was wondering if you could talk a little bit about so when you have your the domain knowledge of the sort of the critical mineral information in your knowledge graph sort of format, what So for me, when I've done work like this, one of the real benefits has been able to write really complex queries and sort of query the data in sort of very unique, very sort of complicated ways. I was sort of wondering, what are the end use kind of complex queries that you're thinking of targeting here?
Yeah, actually the queries end up being fairly complicated. And we haven't written all the queries yet that we'll need for this project, but because what happens is that we have this notion of a mineral inventory, and we organized it this way because when you go to extract the information from the mining reports themselves, the information that's contained in the mining reports will include things like inferred in terms of, you know, they've estimated that there's this much material here, indicated where they've drilled holes in this material. But then they also have this notion of sort of resources, which is that they've actually determined that there's a certain amount of material that's economically viable to extract from the ground. And so they use all these different terms. And so one of the nice things about, you know, having a whole query language to do this is that there's not a single answer in terms of the amount of material in the ground, right? So the queries themselves, so some mines will only have inferred and indicated information, meaning they haven't actually determined what's economically viable in this mine.
Yeah.
And so what we'll have to do is write a query that says, okay, if you don't have resources, then tell us what the inferred and indicated indicate, and then we'll estimate that. And then you have to also look at the previous years where this mine was operational and sort of say, okay, and there's another set of information that's what's called extracted, which means that it was extracted from the ground. I don't think the details are actually important here. What I was trying to get at is that, you know, we have the ability to write fairly complicated queries across this data because the data itself is fairly complicated.
Yeah.
So to actually get the total amount of material for an estimated mining site, it's going to be the sum of the information of all the values that were extracted in previous years, plus the combination of either the inferred and indicated or the total amount of resources. And you can write that. I mean, you can write those kinds of queries and stuff. And
All right.
you know, that will be, you know, not always simple to write, but the nice thing is that then as new information becomes available, it just gets fed in the same queries. So once you write those queries, then they will just continue to do the right thing as more information becomes available.
That's great. Thanks very much.
Yeah. So I mean, Sparkle is a lot like SQL. If those of you are not familiar with Sparkle, it's essentially a query language that you write across triples, and so you can write these fairly complicated things. And you know, one of the things we're interested in is being able to do complicated sort of spatial temporal queries. In this case, it's more temporal because you're doing it over time, but in other cases, you might be doing sort of more complicated kind of spatial queries where you're trying to aggregate information across a given area and stuff. That's one of the areas that one of my PhD students is working on.
Yeah, that's great. Thanks. Actually, I had one other question, if you don't mind.
Oh, please.
Yeah, go ahead.
Yeah. So, so I've done a bit of work for mining companies before, and I was one of the people doing the soul crushing work of transcribing all of that information. And especially for like data from junior companies, the data quality can be really bad. And I was wondering how have you tried to approach data quality, sort of validation, or uncertainty quantification?
Yeah, I think that's a great question because I think this is really important and one that has come up in our discussions with the experts and stuff. And one of the things I didn't talk about is that I think we're going to have a representation of the data in terms of sort of what's called conforming and non-conforming. So the conforming is information that's come out of some kind of reputable source where there's, you know, where they believe the data has been validated. So the Canadian reports, the 43101 reports, the information that comes out of those would be sort of considered conforming information. Whereas if you go to the company's website and you scrape some information from the website and you sort of say, oh, this is the amount of material they claim they produce, then that would be non-conforming. And so the plan for dealing with this is we're basically going to, in our representation of the data in the system, we'll indicate whether or not we believe the data is conforming or non-conforming. And then when we go to actually produce the gradient tonnage reports, we'll be able to sort of say, okay, let's create a gradient tonnage reports with just the conforming information, so we can see that what we think this looks like. And then we can also try to create one with the non-conforming information, with the recognition that some of that information might be wildly inflated. But oftentimes, according to our USGS experts, it's easy to see the data that sort of looks like it's been inflated, and sort of treat those as outliers. But simply being able to know, okay, that you have some information that's conforming and some other information that you may want to bring in that's non-conforming to see what it shows, but taking it with a grain of salt.
Yeah, I mean, it almost sounds like it admits a Bayesian approach.
Yes.
Yeah.
Yes.
That's a whole different thing. Anyway, thank you very much.
I mean, so you could do some automatic sort of analysis of the data. I haven't really thought about that yet, but that might be a way to go too. And we haven't, we'll have to see what the data actually looks like as we pull it in from all these different sources and stuff. But I think you could extend it so that you do some evaluation of the actual data and sort of throw out the information that looks like it just isn't likely to fit the model.
Anyway, thank you.
Yeah, good questions. Thank you.
Yep. Anyone else? Yeah, I have a quick follow-up question. Just one additional to what William Dempsey just asked. I think you're using large language models, the GPT, to extract information from reports. I think you've already done a really good job. Like for the data source, for the reports you're going to extract data, you get those from authentic, reliable sources, like from USGS or some other. But once you see the results get from GPT or large language models, do you already see a systematic way or other kind of approach to verify or validate the result generated by the large language models?
Yeah, that's a really good question. I think one of the things that we plan to do here is build a user interface where we record where all the information came from, to make it really easy for an expert or even the builders of the system to quickly sort of do the validation, right? So it depends on what level of validation we're concerned with here, but I think that one thing that's relatively straightforward to do is to actually be able to record exactly where the information came from. And in fact, I tried this and it worked pretty well, where I could actually ask the system, okay, show me the sentence where this information came from, or show me the paragraph where this information came from. And then you could go and look for that information directly in the report and stuff. So this can help address the hallucination problem that sort of people talk about with large language models and stuff. But then the other piece of this is then providing some kind of UI so that where the expert can basically quickly drill down and sort of say, yeah, is this really accurate, right? Is this the right place in the report to have gotten this information?
I see Kate raised her hand. Kate, yeah, you can ask your question.
Yeah, hi, can you hear me?
Yeah.
This microphone's working? Great. Yeah, I was just wondering, so isn't that just some information that you could just annotate, like each sort of like data record with, right? Just as an annotation, the source of the data is where it came from, so that they'll be easily queryable as well, right?
Absolutely, that is the plan. So if you look at in the schema that I showed you of all the data, so one of the records is for every given sort of inventory record, which is the information about the gradient tonnage extraction report, it links to a reference, and the reference is the publication combined with the number and then the bounding box, the information on the page. And so the idea is that we would store that data record with all the extract information, so it's directly there. But of course, storing it's not enough, right? You need some kind of UI that then allows the user to actually be able to quickly drill down and sort of say,
okay, all right, I see what you're saying. And I was just gonna say, it's interesting that I hadn't really thought about, like, to be able to give that level of granularity where you can say, like, this came from like this page, this line in the text would be probably really helpful to people as well. So
exactly, but more helpful if you could show them the text.
Yeah.
Okay, so taking into account about time, we probably need to end it here. thanks
Okay.
again to Professor Craig Knoblock for your time and this wonderful talk.
No, my pleasure. Yeah. And, if anyone's working on this topic or interested in learning more, reach out. We'll be publishing some papers soon about some of the work we're doing here.
That's great. Okay. I will stop recording it here.